Welcome back, everyone. Yes, I know. I know you got excited outside, didn't you? All these people are still out there. And don't think that if you got back in here on time that you're blameless. I observe things, and I noticed that there are people who are here now who were outside being interesting before. So, you know, the delay is partly on you. And by the way, how good were the scones? Yeah, I mean, see, I say that because when you've had a bad scone, it's kind of unforgivable. Whenever I see them at an event, it's like, oh, you're putting a lot of pressure on yourself now, but these were cracking good scones. And I probably didn't steal very many of them. Okay, let us turn our attention to our next speaker. He has a research background creating simulated universes on supercomputers to understand how galaxies form within vast clouds of dark matter. He's currently the Vice Chancellor of Flagship initiatives at Swinburne University of Technology, bringing together diverse research teams with industry and government stakeholders to undertake transformative programs in a wide range of sectors. Now, I've eaten the scones, I've drunk the coffee, I know that there's no excuse for a lack of energy. Will you please put your hands together and welcome to the stage Professor Alan Duffy.
Well, thank you so much for that rapturous applause and welcome and kind words. I am going to try to sketch out what research infrastructure may look like beyond 2050, which is obviously an absurd challenge, and it is one I am, particularly in this audience, uniquely ill-qualified to present. So I'm going to lean back on my strengths, as most other researchers do. When they are asked about the generalized future for research, they are, as an astronomer say, astronomical facilities. If it's microscopy, well, we all know the answer there. So I will try to stay in my lane to a certain degree, but also broaden those lessons a little more generally. Before I do, I would like to acknowledge the traditional people on the lands of which my institution, Swinburne, is based, the Wurundjeri people of the Kulin Nation. I'd like to pay my respects to elders, past, present, emerging, and of course extend those respects to all Aboriginal and Torres Strait Islander peoples. I'd actually also like to acknowledge and thank the organizers for this incredible event, but also for their efforts to ensure a rich diversity of First Nations views, thoughts. Attendances were encouraged, were made possible, I believe through some support as well. This has been the better conversation, the much more enriching and valuable for their participation, and I hope we just continue to see that grow. So I just want to both thank the First Nations attendees, but also, of course, the organizers for recognizing, valuing, and encouraging that attendance. Now, if we cast our minds back some billion years ago, a cataclysmic event occurs, the nature of which is actually still unknown. The light travels out, a century's worth of the output of our sun in the blink of an eye. And it travels through the universe on its way until finally it hits this telescope, the CSIRO Parkes telescope. Now, my Swinburne colleague, Matthew Bells, was in the control room at the time, talking to his then student, Duncan Lorimer. That was pretty boring, pretty regular observing room, which meant they had lots of time to look back into the data. And Duncan said, I found something a little strange. In fact, I'm not sure it's real, it's just too bright. So they looked and they looked. About a year of trying to test and understand and rule out everything, including microwave ovens as the source. And eventually they were able to demonstratively show that this event in the data was real. It was known as a fast radio burst. It was not alone. There were more of them in the data. You just now had to know what to look for. They were recognized, along with Moira McLaughlin, at the Shaw Prize last year. It's actually Asia's Nobel Prize. I like this story because, for one, it gives my institution a plug with Matthew at Swinburne. I particularly like it because a facility that was built in 1961, 60 years later, made one of the biggest discoveries in astronomy. And that, of course, was through upgrades, through constant reinvestment, capital and human, in this facility. I like this story because the data was available, was archived, was open, the FAIR principles we've heard about. Now, this has been an incredible success story. Astronomers, of course, and this is about research infrastructure, are greedy, and we go bigger, and you've already heard this many times at this event. We now have, of course, the Square Kilometre Array Observatory. One point that hasn't been shared yet about the SKO is that because of the sheer torrent of data, we don't get to save the original files. Unlike at Parkes, we will have to do various quality control, various distillation, if you will, of the data sets. We've heard of terms like interferometry. There are other higher value add data product steps that are required just to reduce it down to the hundreds of petabytes of data storage required. So in other words, if we haven't designed our approach to search with sufficient flexibility today, quite literally the AI that we are designing today, that will determine what we think the universe looks like tomorrow. And that's a very uncomfortable place for astronomy. We've never had to make that choice before. We've always been able to go back into the archives and re-examine it. The other reason I'm referencing the SKA is the fact that I got to write about it. And I know some people have been plugging books, so this is my attempt. I was very fortunate to contribute a chapter to this, the team led out of CERN, but this was around the big science projects and the innovations that they drove. And what I found fascinating was when I looked into the SKA as one of my examples, LIGO was another, we had been talking about it since the 90s. So it took about 25 years, once we got really going, to see it delivered. And that's very helpful, because that's just about the amount of time we have now looking forward to 2050. So on the one hand, this research infrastructure at 2050 and beyond, well, that's not too long at all. It's just one mega facility. On the other hand, in academic lifetimes, it's 6 generations of PhDs, which I find just an astonishingly intimidating thought. What will those PhDs be needing by that period? The audacity to plan today to deliver then is a humbling challenge. So I was beginning to think about the trends that we are seeing. And as I said, scientifically speaking, as an astronomer, as an astrophysics trained professional, I am a hammer and everything is a nail. So one of those trends is rockets. I also set up the Space Institute, so I have a particular love for rockets. Rocket launch costs are drastically reducing. We are seeing payload delivery costs being reduced by orders of magnitude in just the last few years. There is no reason to suspect that trend does not continue for at least another order of magnitude by 2050. This doesn't need space elevators. This is just bigger and better, more efficient rockets, better use of the payload capacity, and most importantly, the improvements of the performance of the satellites that you send up. So performance per kilogram, they are also undergoing orders of magnitude improvement. We have the large space agency delivered programs, of course, the likes by NASA of Landsat, which I'm very proud to say Australia has committed to the next round of. The Sentinel fleet under the Copernicus mission of the European Space Agency, which have exquisite data sets made publicly available. We then have an astonishing growth in the commercial sector, provision by, for the sort of the gold standard, if you will, of the last generation satellites by teams like Maxar, where there are large, bus-sized, if you will, satellites sitting out at geostationary orbits very, very far off. And of course, the new revolution is in small sats or CubeSats that are closer to the Earth. They're closer, so you don't need as good optics to see the same kind of resolution. The problem is you whiz by very quickly, so if you want to start to cover the Earth, you just need to have a lot of them in orbit. Planet Labs is perhaps the best known example of this, where there's now 200 of their small sats operating, providing near continuous coverage of the Earth. This is an astonishing transformation. We are now experiencing video from orbit, HD. Take a look. It's by the Vivid Eye team. For some reason, I can get the YouTube to embed here, but you actually see just a video of this thing from space. Now, no one needs that. I mean, like, it's just a ridiculous, unnecessary, but very cool demonstration of technology. But what about by 2050? The ridiculous, absurd, over-engineered solution of today is the absolute need of tomorrow. So I would suspect, and I hazard a guess, that with the continuing addition of satellites in orbit, the development of their cameras, their optics, their sensors, moving into, for example, hyperspectral, perhaps in HD video quality or whatever we're using by then, of a 24/7 capacity, constant monitoring of the Earth in a range of optical and infrared wavelengths for a range of ecological sciences, but also using synthetic aperture radar, or indeed even interferometric versions where you can get millimeter change detection from space on the ground. This is an astonishing era that we are seeing underway, and by 2050, this revolution will be well and truly ubiquitous. However, and I was very pleased in all of the references to this fact, without the ground truthing, all of that data is just so much, speculation is a little strong, but the more ground truthing of those satellite images or other data products that are being derived, the better. When you have distributed sensors across the land and in the sea, you can tie that data from space down to what it means on the ground. So very pleased with the CSIRO initiative, together with SmartSat known as AquaWatch, where they're providing that marine quality testing. I'm very proud, in fact, of our institution, which has extended one of those monitoring facilities to Malaysia, which has, as far as I'm aware, in fact, I think we're the only marine sampling location in Sarawak, which is actually kind of disturbing. And it was referenced in one of the talks that where you have ground truthing is a historical fact. It's where the rich countries are. That's where our sensors are. Argo and other distributed ocean measurement points, they have a much more global footprint. But it's fair to say that when you tie down the satellite data to the ground for all of your environmental, ecological, and other studies, the data quality is going to be better as it exists today in rich countries than low and middle income. Unless we put more ground truthing sites globally, we will embed that disadvantage, the disenfranchisement of the rest of the world. So global research infrastructure truly does need to be global. We have the satellites that are orbiting. We need the measurement points on the ground to be so too. That will unlock the future by 2050. We already have its glimpses with examples like NASA's observation programs. This particular instance, Eyes on Earth, is just a glorious visual that you can watch the video play of all the different data streams coming through and the data products that are being developed. Together, in one of the sessions, we had Shelby Walker and in Paula's panel referencing the digital twin of the ocean initiative, where, as the name implies, we will have all of those distributed sensors, both that are in the water, but also on the ground through distributed acoustic sensors, or optical fibers, that essentially allow you to, through the tiny variations of the reflection of the light along that fiber, caused by changes in the water pressure as it pushes on or other environmental impacts, you can begin to turn the optical telecommunications network into that global distributed sensor array. So if you tie together everything that we have in the oceans, projecting forward, you tie together everything that we're getting from space, projecting forward, you bring together your digital twin ocean and your digital twin Earth, and you have your digital twin planet. A unified data frame that a range of science disciplines can use, and not forgetting, of course, my geophysics colleagues, who probably would like to be included in that digital twin of the entire planet. And how will we get there, particularly for geophysics? Well, quantum. So another of our trends. I didn't actually hear that much about quantum at this, which I kind of find interesting. And I don't mean in the quantum compute side, although by 2050, I'm sure there'll be tolerant-free gates, and we'll have actual true potential quantum internet, but quantum sensors. So the improvement of our sensors to, in astronomy's case or image case, to single photon detection, from optical down to microwaves, maybe even lower, to for example, use of quantum diamonds, we can have magnetic field detection, activity of the brain, improved spatial and temporal resolution, seeing the thoughts, if you will, as they occur. We're already using some early stages of this at Swinburne to try to determine seizure events in advance. It's an enormous data challenge, and we haven't even got yet to what that quantum future will deliver. For geophysics, quantum accelerometers, as measures of the gravitational field, will allow us to probe kilometers of depth of the Earth's crust at exquisite resolution and stability of performance. So all of these new sensors will, of course, as we've been hearing many, many times, be used by the ever more impressive compute facilities. Now, one thing that I want to highlight, just look out for this, if you're not aware, is quantum networking. Hands up who's heard of quantum networks. Our chief scientist who led the quantum strategy has, which is very good. Excellent. Okay. This is well worth me just spending one more minute on. If you have so in this wonderful paper that demonstrated this as an experiment just a few years ago, it's a thought experiment and tested in the lab a little bit, first stage tests. You have optical cavities, so in other words, you have your quantum sensor, and then you connect another optical cavity to that, and you see, are you improving the signal to noise? Now, in a traditional sense, you might get a square root 2 improvement signal to noise ratio. That's not what you get when you do this in a true quantum fashion. Instead, you get exponential growth in the signal to noise of your networked sensors with the just linear addition of those sensors. Eventually, it turns over. Essentially, you just end up correlating fundamental noise up. But can you imagine all of the discoveries we will make when we have 100x, 1,000x beyond what even today's really kind of astonishing quantum sensors are promising us? So just look out for that. That's one of those, I think, absolutely transformative innovations, particularly for the medical sector. This is where you will find lots of those small quantum diamond, for example, sensors being correlated. All right, and of course the big one, AI. So everyone knows it. It's going to, I was going to say it's going to destroy everything. It's going to disrupt everything. Sorry. I mean, it could destroy the planet. Let's be honest. I mean, the energy projection usage is just terrifying. I mean, it's mostly terrifying if we're generating that through fossil fuel-based approach. If it's driving even greater scaling of PV deployment and lower cost per unit as a result, it doesn't have to be as terrible an outcome as otherwise. But it's clear that this is our lab of the future, in which distributed sensors feeding in to large data centers, interrogated through AI, will be the primary means by which research is undertaken. Not by 2050, obviously, this is already happening today, but I mean actually the predominant mode of discovery, I very much think will be this by 2050. Which does beg the question, how do you access that data? Now, we heard from James Wistock about the power in the medical community of the use of AI, but also the challenge. Patient data, rightly, is considered of has immense privacy concerns. I'm very proud of an initiative that the Australia Data Commons has initiated called HASANDA. So this is where we share the data, not of patient data. That really is, I mean, honestly, we will land on Mars, I suspect, before we'll get that particular ethical quandary sorted, but the actual sharing of clinical trial data. Win or lose, positive or negative outcome, whatever it is, if it was publicly funded, eventually we'll end up here. This is going to be an incredibly powerful data set where we just avoid the duplication, the waste of time, resources, and the enormous impact on patients through the repeat of trials. So I'm very proud, very excited about the potential of HASANDA. We have a similar data set that's been running for a little longer by the DOE. This is known as the Materials Project. This is the Google of materials data. So a few 100,000 molecules, well-characterized, or interactions well-characterized. You just literally type in the properties you want. It's kind of astonishing to do. You just type in the properties you want, and you get your list. This is the kind of database that AI will unlock for so many more of our PhD students, all those generations to come. So one of my first takeaways will be this seamless sharing of data from a variety of sources, then experiments. And again, I'm noting in the last panel the discussion around the confidentiality of commercial paid-for research data, at least publicly funded. Those fusion of the data sets and together with next-gen AI will be the predominant means of discovery in the future. Sounds great, could be tricky. So for a look into the future, we turn to the past. And this is the actual last book plug, I promise. Suji Sheehy, a wonderful medical researcher at University of Melbourne, wrote a book. I highly recommend it. And I mean that literally because I think I've actually written something for one of the cover sleeves in the Australian market. And it's called The Matter of Everything. And in it, she goes through key experiments in history and really into the lab itself, the environment, this wherever possible, hearing from the researchers and other means of discovery, to understand how it happened. And the importance particularly, and in fact the ubiquitous finding from all dozen world-changing experiments, was the professional technical expertise in those labs. Yes, there's Bragg, but there's his team. And that's the kind of challenge I see ahead. As we move to this era of abstract data or experimental exploration through AI, the researchers are no longer connected to the research. It is through the AI that they perform that investigation. And that's fine, because that's what happens. Commoditization, the ability to deliver ever easier use of tools, that's how we have advanced. I had one software package when I was undertaking my PhD, and I was in there, it was in C, God help me, at one point it was a Fortran 77 actually, but anyways, I got out of that. 4 computer scientists laughed at that. My PhD students today cross-validate against 5, and they do an exploration of a search in parameter space hundreds of times larger than I did, and that's fantastic. But as a result, rightly, they don't spend as much time in the code. So this challenge of how do you retain technical excellence, expertise for the equipment, for the digital equipment. We had a wonderful panel session discussing the digital workforce, and Rosie Hicks from ARDC showed a wonderful matrix about the skills required, as well as the training modalities that you can deliver, at least for the Australian context. So I'd encourage you all to look that up. We also had a recognition by NASA's Kartik Sheth about the importance of that human capital. And yet, it's still not funded. Certainly not with the career progression that the value it demonstrates this human capital deserves. This at least is Australia's challenge, and it has been said many times at this conference, and I'm heartened by the number of large research infrastructures that are worrying about this. But how to retain expert lab technicians is one of the things that keeps me up at night in my portfolio at Swinburne. So that's the second takeaway. Paradoxically, the rise of AI only increases the value of the deep technical expertise. And we do not have funding systems that provide a career path. Not as easily as academic paths, at least. And let's be honest, even that's not easy. So it's a challenge. I know we all are aware. I just think it's actually even worse than we have been sharing at this event because of how AI will disrupt our means of data exploration and discovery. Now, speaking of lovely bits of equipment, and we've heard a few times about synchrotrons. This is Australia's. This is the ANSTO synchrotron facility in Melbourne. I love this facility because it has a very flexible model of usage where, thanks to the beamlines, you can provide cutting-edge discovery, install new sensors or new types of interrogation using that centralized beam source. So this is, by its very nature, has the ability to be upgraded through its lifetime. They are accessible because they have both intern programs, fellowship, travels, as well as, of course, online access. And they invest in their teams and deliver technical training. And indeed, we've heard how the European, by Ed Mitchell, just before, delivers a similar training at their synchrotron. One challenge is sustainability, and we've heard it being referenced in different ways. Sustainable in a financial sense. These are extremely expensive pieces of equipment. The new version of the synchrotron will be $1 billion. That's an enormous amount of money to ask. So how do you build financial sustainability, delivery of upgrades, of workforce development and training? How do you retain the public support for such an investment? These are, I think, questions that keep us all up at night as well. Now, with the direction of travel, it's fair to say that as our technologies become more advanced, certainly in these large facilities, they are becoming more expensive. And as a result, they're also becoming more concentrated. By which I mean, if you imagine the partnerships required to now deliver these synchrotrons, we inherently are talking about multinational initiatives. It used to be one state competing against another. In the Australian context, now it's all the states together, and now it's beginning to become our international partners. So you are taking distributed resourcing, and you are by its very nature concentrating it. That is the nature of an infrastructure program, but it is extremely concerning if we don't build in how we feed back into the system, the extended network, and we've heard this many times, very pleased indeed, how many times we've heard about just how important it is a true ecosystem and not a one-way transfer of resourcing, talent, and capital. So sustainability is certainly forefront in my mind, which is why I fell off my chair when we had Masaki Takata from the Photon Science Innovation Center in Jane Fitzpatrick's, the CEO of AMP's panel, talking about nanoterasu, which has been 50% privately funded. No idea still after his talk how he managed to do that. That is just, that's almost like robbery on a bank robber level of enormous infamy. And I don't know how he was able to get those kinds of commitments, but he showed value, obviously being somewhat silly about this, but the value he was able to demonstrate to those companies, to the industrial ecosystem in Japan, they could see the value and they could invest. That, I would argue, is a challenge to all of us as major research infrastructure operators, or even just cheerleaders for. How do we get greater private investment? Because let's be honest, the government budgets are not increasing. Some of you may be lucky enough to be in a country where that is the case. We have a chief scientist here, so I'm just going to say, Australia, you can fill in the blanks. We're cool though, right? You and me, we're still okay, right, Kathy? So, third takeaway. As it becomes more advanced, it becomes more expensive, and by that very nature becomes more concentrated. So we need to redouble our efforts to ensure we have connectivity back into the ecosystem, retaining those connections that build the public support, the industrial interest in continuing those research infrastructures. Or don't. That's the flip side. If that's not the approach, we need to lessen our ambitions. Right? There is a choice that we have to make, but we don't always have to go bigger. Maybe that's not the right model at all. And I'm interested in how we might see research infrastructure addressing the SDGs, and obviously we've had some panels on this, which have been fantastic, but not just in terms of how we put solar panels on the synchrotron. It's great, that's 20% of the electricity provision now directly through those PV. But how do we use the research infrastructure in a targeted manner to deliver on the solutions we need now? Focused approaches to collaborations between government, industry, and academia to deliver on these innovations as and when they are needed, which is to say now. So anyone who knows me I'm a fan of the missions concept. Australia co-leads, as part of the International Energy Agency's mission innovation, we co-lead the clean hydrogen mission and the net zero industries mission. We're involved in a range of others. What I like is that this provides that top-down directive. We've heard in various panels about the importance of both grassroots, but also top-down for longevity, for something of a leadership role. I would suggest to government in the room, this is not a panacea. You don't just say, we've got a mission, right? That cascades through all of government, all of sector response, but then you have to stay involved. And leadership's exhausting when you have to go along with the work. It's great to say, point in the direction, go, but obviously being a part of that journey, a committed part to that solution is a challenge, and it's particularly a challenge with limited term limits, right? Priorities change, and that's fine, that's absolutely correct. But these are big problems, and will not change in a 3-year political cycle. So how do we build in continuity of commitment? It's obviously a much bigger challenge than research infrastructure alone, but research infrastructure, particularly of the larger scale, is the thing that remains. Right? We're still here, new government, but we're still here. New funding agency or priorities change, but there is inertia in the system. Which all sounds well and good, but we have a challenge, and that is we don't actually collaborate well at all. I mean, I think everyone's here very lovely and they're all collegial, but as a system, and I can tell you why, I can confidently tell you that we don't collaborate well on the scale to drive world-changing missions, because it's so hard and costs so much money to do. We work really hard at this, and we do not have an inherent collaborative approach, not in the way that we want. So we turn to organizational psychology, ecology, social scientists, and we say, what can we do to be collaborative by design? Grassroots, fundamental, all of the nudge economics driving us in that way. I would encourage you to quickly take a picture of this. There's a wonderful, so Turkin's work is fantastic. There's actually just a very readable publication, which I've summarized, the dot point solutions, but the paper is well worth reading. It essentially uses multi-level selection theory. But what I really like from these dot points are they're quite tangible tactical approaches. And it's about driving a better behavior from inception. So yes, weigh the group outcomes as opposed to the top of the leadership. And let's be frank, awards, grants, high size, dare I say, all of these are metrics that drive us in the opposite direction. Not uncorrelated, but not as collaborative as it could be. The support positions we've already heard about, technical staff excellence, but there's a rich variety of challenges in research infrastructure beyond the technical. So EDI, engagement, outreach, contracting, these are really valuable roles, and they learn the specifics of their research infrastructure ecosystem. And they get better at it, and we should retain and should value them, and if they want to stay, we should be able to retain them. We have some wonderful example of the Templeton, for example, with this group level competitions where you're actually trying to structure it as a group, because we all love a challenge. Scientific policing, hate to say it, but sometimes researchers under the pressure can exhibit poor behavior. Let's be honest, this is the challenge. A number of retractions are just continuing to grow, so we need to recognize the challenge and invest to resolve it. And then this measuring indirect contributions. We even heard in the last session, we don't know the value of the people that we train when they go off to industry. And that is arguably for research infrastructure some of our greatest contributions. Certainly as a university it is, to the impact we have in the world. Final point on this, if you don't know, hands up, who knows the price equation? Oh, so please. Well, obviously I'm now going to say, look it up. The price equation is the actual mathematical formulation which takes in all of the collaborative and competitive aspects of an ecology, of a company, of an organization. And it gives you a direction. Will it be a more collaborative or competitive or combative process? So this is an astonishing bit of work. I just encourage you all, obviously these papers, but then the price equation, if you want to know actually how you can start to do predictive modeling with the tools that you implement. And that is the fourth takeaway, that we have as big challenges, we require these all-of-sector mission-like responses. But that only works, or at least it will work better, if we are collaborative from the ground up. If our systems are built to reward, not punish. It's not supposed to be volunteerism, to sacrifice your career to engage with research communities or others who can deliver on that larger impact. Not sure how long left I have. 5 minutes? 5 minutes? Does anyone know? 5 minutes, thank you. So I'll rattle through just a couple of little plugs. So the UN Sustainable Development Solutions Network has some wonderful case studies, some concepts of what the 2050 future may look. I'll just plug the Amazon Innovation Hub as an example. This obviously with a focus on biological research, but connecting the rich diversity of the ecosystem together in the size as well as the geographical distribution of those hubs. So this is one way to get around the concentration, inherent concentration I mentioned of the mega facilities by investing in the ecosystem. It is an idea of how we could do better and have a structured approach to distributed scientific discovery that also delivers translation outcomes. So I have a couple of questions that I ask myself, and certainly I hope, and I'm sure you all do. So one is, as technology progresses, how do we retain that cutting edge in terms of our facilities? And also I challenged you actually need it, or at least you need all of it in-house. So through partnerships, of course, we know we can have access to it. I have a science communication interest, so I'm certainly well aware of the challenge of public support for the infrastructure. And despite how much you love your piece of equipment, I guarantee the public doesn't as much, right? That's a challenge. And ask yourself how you will support your communities, companies, and countries in developing, because again, it's either taxpayer, industry, or just fundamentally through government funded. Well, one way, with my current hat on, is certainly through industry collaboration. The CSRO does a wonderful job at this. It co-locates with industry where it can. It brings in a range of technical expertise, and it has a very much industry-aligned, industry-facing engagement program. It's our national science agency. It's involved in the SKA, as we've heard. It also tries to solve very much tangible challenges today. There's Helen sitting in the Mining Resources Centre over in Perth, the data robotics team right here in Brisbane, with lots of cool gear, and also the hydrogen refueler, which Swinburne is a part of in Melbourne, designing training courses for safe utilization of hydrogen. We're not doing electrolyzers there, we're just trying to figure out how you safely operate. So it's a supply chain or value chain approach, trying to anticipate those challenges. Because we have this absolute constant challenge between the applied and fundamental. This is the constant debate in Australia, I'm sure it is worldwide. Why would you fund fundamental research X when we have applied research Y need today? And we know it's a pipeline, right? We know the fundamental will lead to the applied. Today's fundamental is tomorrow's applied. That balancing act is, I'm pleased to say, something I've seen firsthand work very well. We saw a little discussion of this with Elizabeth Barberio from the Stawell Underground Physics Laboratory. This is her leadership also of SABRE, the dark matter detector, the first in the Southern Hemisphere. This is the tank as it got delivered to my lab in Wantirna, a vocational training college. Barely fit through the door. I didn't measure it that well. We have this now going underground, and we saw some slides, but if you, a kilometer underground, when you go into this lab, you've got kind of this tunnel that you're winding your way around in the dark and the humidity. And then you turn a corner and there's a ginormous clean room vault door, and then it's a cathedral high thing. It's just the most, as a cognitive disconnect, it's really kind of astonishing. So it's open for business. It is the cleanest, most radioactively quiet location in the Southern Hemisphere. And by the very concentration of physicists, geophysicists, actual mining engineers, we also broke into the applied. So very much fundamental, searching for dark matter. But as a result, I'm very proud to say, I was part of a spin out of some IP from this, where we use those particles of space that we're trying to escape by going deep underground to act like an X-ray scan of the rock around, where denser ore bodies block those muons, casting shadows, very much like an X-ray. From those initial connections, collaboration, the ecosystem that supple formed, we were able to generate a spin-out and ultimately take scans of tailing storage facilities, so the walls that hold back the output waste of mine sites. So huge environmental challenge. We can do better scanning and hence safety of those sites. This is the kind of technology that comes because you got smart people together. There's no way you would have planned for this. You wouldn't build a dark matter detector a kilometer underground on the hopes of a mining company-related spin-out, right? So we can get translation. We have to just be acknowledging that. Now, I wanted to give a story about, SpaceX and NASA, because I keep hearing about it. All I'm going to say is this is a collaboration now, where SpaceX is drastically reducing the cost of launch, certainly in comparison with the SLS. It allows NASA to retain the International Space Station as a site for experimentation. In fact, it is now so cheap to get the space station. We have a national schools program operated out of Swinburne, where we take high school designed, built experiments to space. That is astonishing. That is wild to me that is something we can offer today. The space station has a limited lifetime. The future will be a private space company, very likely Axiom Space. Again, freeing up NASA to do the deeper discovery missions. Along the way, the industrialization of low Earth orbit, we've already heard about this, it was a great discussion with Fabio and Ximing. This gets in the way of our telescopes, optical. It also gets in the way of the radio telescopes. And one solution by Ximing was to go to L2 or just go off-world. I'll take him up on that if he wants to fund the Lunar Crater Radio Telescope, a genuine NASA concept. Go on the far side of the moon, protected from all that radiation from radio interference from space and the orbiting constellation of satellites. And there you can observe the universe. Sounds exciting. As we heard, there's some technical challenges, but by 2050, just saying, by 2050, one mission that will happen is that we will land on Enceladus or Enceladus. This is a Saturn moon, an ice moon, very likely with life beneath the icy crust, and the European Space Agency will have a craft that will land on the surface and directly search for life. That is planned by 2050. So that's what the future looks like. We discover life beyond Earth. I'm going to leave you with some thoughts. Infrastructure, it is not just the equipment, it is the network, the entities, the companies, the people it brings together. And those people, the human capital, are the key to continuing to reinvest in their growth and particularly in this AI future. We have relevance because we serve communities. We also have a history baked in. Where we are deployed, what we've deployed, that is a legacy that we need to acknowledge, and particularly where it's ground truthing, we need to address. There are other, of course, sustainable issues. And for those who were fortunate enough to attend the Indigenous evening last night, an Indigenous astronomy evening, we heard a story from General Wajiri Yamachi, elder, where in partnership with the CSIRO, they walked the land and they discovered that there were sacred sites along where the square kilometre array baselines, so essentially these antenna arms, would be outstretching over tens of kilometres. And such was the depth of the partnership, the true commitment to the Indigenous custodians of that land. The entire antenna array was moved around so that there was no disturbance. What that means is we will be exploring the depth of space, literally the edge of the universe, with this telescope, respectful of the land on which we exist. That connection of sky and country that is embodied in Indigenous practices. I'm very proud that Australia was a true partner in this, and that our view of the universe genuinely has now been orientated to accommodate, to recognize the first astronomers on this land. And with that very positive hope that we can see more of that in the future, I will thank you for your time, and I'll thank the organizer for this opportunity.
Thank you, Alan. Well, indeed, we are at the point now where we're rapidly drifting. It's like a tide towards the end of the conference, but don't go anywhere yet. It's okay. We have people to save you from drowning. After 3 days of hope and insight and argument and vision and sharing, it's important and perhaps it's exciting, in fact, to ask, what does it all mean? What next? Let's face it, tomorrow morning you're going to wake up not at this conference. And you're going to have a life, and you're going to have to do stuff, and someone's going to demand you commit to your annual planning. Conveniently, those are big, scary questions, but we have people who can answer them for us.